Hello and welcome back. We have understood how stochastic gradient descent can solve the memory issue with the gradient descent. With this, we can say stochastic gradient descent can solve both the issues, the dummy variable trap as well as memory issue. So we can use stochastic gradient descent on huge volumes of data, even the big data datasets or big data environment also. You can use models built on top of stochastic gradient descent. This is where the deep learning starts. In deep learning, we'll take the stochastic gradient descent algorithm and try to build complex models with logistic regression and other activation functions. We'll discuss more on how to work on huge volumes of data using deep learning in deep learning sessions. But let us try to understand why this equation is giving you the slope of the tangent at the given theta. Suppose your hypothesis function is theta x, only one variable, no intercept, then the cost function for one record becomes y minus h of x whole square or h of x minus y whole square. The actual value minus the predicted value whole square. It's a squared loss because we wanted a convex function so that we can find a place where the tangent is 0, right? When the tangent is 0, that means that's the global minimal error and the theta is the best theta on x-axis, right? So if you take this the squared loss function and then expand it, it becomes y square plus theta square x square minus 2y theta x. And we know that the derivative is the slope of the tangent, right? Because we try to do a tangent to the convex function. When you are trying to do a tangent to the convex function, the dots are going to be very close. The h is going to be very small. J of theta plus h minus j of theta by h when h is almost equal to 0. That is, limit h tends to 0. J of theta plus h minus j of theta by h, that is nothing but derivative function. We have seen that. So we can calculate derivative of this cost function and say that is the gradient or the slope of the tangent. So when I try to do derivative, I am doing partial derivative here. When you really use the gradient descent algorithm, you will be doing multiple linear regression. In there, you will have many thetas. So you need to take derivative of the cost function simultaneously on different thetas. So when you are trying to find a gradient for one theta, you should consider other thetas as constants. That's where the partial derivative is going to help. That's all math. No need to worry about that. If you understand whatever I am showing here is more than enough. So I took the derivative and I expanded this, right? Dou of y square divided by dou theta plus dou of theta square x square by dou theta minus dou of 2y theta x by dou theta. When we are taking derivative with theta, all the other terms in the equation become constants. Constants derivative is 0, right? Dou of y square by dou theta is 0. And I said the other terms will become constants and theta is the variable there. So theta square's derivative is 2 theta, x square is constant. So x square 2 theta. And then here dou theta by dou theta is going to be 1, 2yx. If I take the 2x common, it becomes theta x minus y. That's what we did here. X into theta, right? X into theta minus y, right? In the brackets. So here we took transpose here and we did not take transpose here because the dimensionality of the x matrix and y matrix are matching to multiply. So we did that way. Right? I said logit is equal to theta transpose x. It's a convention. If your x matrix matches the dimensionality, you can directly multiply the x with thetas to get your logits. If the x dimensionality is not matching or you are considering each row as a vector, then you need to do the theta transpose x. Okay, this is y cap value, subtracting y value and then multiplying it with the x. I showed for one record here. When you do it with the whole matrix, it's going to be a vectorized implementation. You will get the gradient for using all values also. We use the same formula in gradient descent also, but we did it with whole data there. Here we are doing it with one record because it is stochastic gradient descent. That explains why this equation gives you the slope of the tangent and then the slope of the tangent we are going to subtract by multiplying with eta, and here eta is learning schedule. To reduce the jumpy nature or the randomness in the cost function, we are trying to reduce the alpha, the learning rate, with each iteration. In the first iteration it may be 0.000 some number, right, maybe 6. In the second iteration it becomes 0.000555, something like that, right. With each iteration the eta learning rate will reduce, because so that the jumpy nature of the algorithm can be controlled, and when it reaches the global minima the jump will be very less, right. I said the stochastic gradient descent will reach the global minima, but it is going to jump around the global minima, right. So when it is jumping around, the jump should be less, so that it will constrain or stay close to the actual global minimum, right, global minimal theta. Okay, I think you got the point. Next section we will try to understand with an intuitive graphical example on how the gradient descent is working, stochastic gradient descent is working. Thank you.